Hello everyone. This video will help you to define the basic quantities required for a two-dimensional random variable in a continuous case. We will see the required definitions and the conditions or criteria to solve any problem in a two-dimensional random variable in a continuous case. As such, a two-dimensional random variable can be classified into a discrete case and a continuous case. We call the case to be a continuous case when the random variables x and y have been defined over a range. So when x and y have been defined for a range of values, say 0 less than x less than your value a, and a quantity called as b less than or equal to y less than or equal to c. Say, if x can vary between this range, if y can vary between this range, it doesn't take any point values, but it takes infinite number of values in this range, in which case you cannot add the data as one by one. So the only way to accumulate the data is going to be through integration. So the integral will help you to find or estimate the values for the random variable x and y. Now going on to the definition, we say the joint PDF of a continuous two-dimensional random variable is going to be satisfying the two conditions basically. The first condition being f of x comma y must be greater than or equal to 0 for all the values of x and y that belong to your range space R. Now second condition is that integral from minus infinity to infinity f of x comma y dx dy must add up to the value called as 1. So the first integral varies for your x, the second variation is that for your y. So you integrate once with respect to dx and the second time with respect to dy. And the total value of both the integration, the double integral, must be equal to the value called as 1. If these two criteria are satisfied, then the function f of x comma y is defined as the joint PDF of the random variable x and y. Next definition, defining the marginal density function of the random variable x and y. Now what do we mean by marginal density function? Now we have been provided with a function f of x comma y, and we want to separate our f of x from that of f of x comma y, or we may need a separation of f of y from my f of x comma y. This separation or pulling out of f of x from f of x comma y or f of y from f of x comma y is called as the marginal density function. Now, this marginal density function of the random variable x is denoted by the script fx, and fx is integral minus infinity to infinity f of x comma y dy. The marginal density function of the random variable y will be equal to f of y, and this is integral minus infinity to infinity f of x comma y dx. Now how about getting this formula? We know that our f of x comma y has two integrals, one varying for my x, the other varying for y, a dx dy. When I want a function of x, what is the idea is I need to eliminate my y entirely. So from this f of x comma y, I am pulling out x alone. So y has to be eliminated. So what will you do is you integrate it with respect to y, substitute the limit of y and get rid of your y entirely. Then you will be left out with a function of x alone. So when you want it with respect to x, integrate with respect to y. In a similar fashion, if your function f of x comma y is going to require f of y, I want f of y. The variable is going to be, now I want in terms of y, which means x has to be eliminated entirely. Now how to eliminate my x? Integrate with respect to dx and apply the limit of x. Then what will be left out? We will be left out just with the variables y alone. That's why we have fy to be integrated with respect to the variable dx. You can remember this formula in this way, like opposite poles attract each other. So when you want a function of x, then integrate with respect to the opposite value, which is dy. Opposite pole of y, you can consider it to be x. So integrate it with respect to dx. So opposite of x is y, opposite of y is x. You can remember in this way, opposite poles attract each other. So when you want fx, integrate with respect to dy, and when you want fy, integrate with respect to dx. Moving on to the next concept, condition for independence of the random variable x and y. So when can I say that my function is going to be independent? So whenever my functions are going to be independent, then what I can do is my function f of x comma y can be split and written as the product of f of x into f of y. This is something similar like for our discrete case, we saw pij to be equal to pi dot product the p dot j. So in a way, this product is going to be the multiplication. Over here also it is going to be the multiplication. So I can separate my fx and fy, provided this fx is marginal and this fy is going to be my marginal of y. When I can express in this way? Only when x and y are going to be independent. So the condition for independence of the random variable is given by f of xy is going to be equal to fx and fy. Moving on to the next concept, conditional probability of x given y. We already know about the conditional probability of a given b. What is probability of a given b? It is probability of a intersection b divided by p of b. We need to remember that when it comes to a two-dimensional random variable, the quantity intersection can be replaced with that of an comma. So what will happen? This can be written as p of a comma b divided by p of b. Now when it comes to the continuous case, your f of x given y will be written as f of x intersection, this intersection will become comma, f of x comma y by f of y. In a similar way, conditional probability of y given x will be f of y comma x by f of x. But we know that f of x comma y and y comma x are both the same. So in which case you replace the numerator as f of x comma y. This f of x comma y is going to be, the numerator is going to be the joint PDF of the two-dimensional random variable x and y, and the denominator is nothing but the marginal density function of either your y or x depending upon which has been given to you. Now moving on to the next one, mean of the random variables x and y. When we defined a one-dimensional random variable, we defined the mean of e of x as x into f of x dx. Similarly, when I want mean of the random variable y, I can define it as e of y is integral y into f of y dy. Now, when I want the mean of the product of the two variables, that is e of xy. So, now there are going to be two variables involved over here. Therefore, you need two integrations. You always have to keep it in mind. When the input has one variable, one integration is sufficient. But when you have two variables as input, we need two integration, one with respect to x, the other one with respect to y. So when you want e of xy double integral, this input is taken as such, then multiplied with the density function. So it is going to be the joint PDF of your f of x comma y, and then you take the integration first with respect to x or y depending upon the limit which has been available to you. So the mean of the product e of xy is xy into f of x comma y into dx dy. In the one-dimensional random variable, we will be using marginal density function of x and the marginal density function of y. That is our fx and fy. But when it comes to two dimension, we will be making use of the joint PDF of our x and y. Okay. So now using this mean, we will be able to define the next quantity called as variance. For a one-dimensional random variable, we define variance of x as e of x square minus e of x the whole square. Now, in a similar fashion, what will be variance of y? Variance of y will be e of y square minus e of y the whole square. Now, if I want the covariance of x and y, now this covariance is denoted by COV of x comma y and is defined as E of xy minus E of x product E of y. What is this E of xy? This E of xy is nothing but the expected value of the product xy which we defined or derived over here. And what is this E of x and E of y? They are the one-dimensional random variables mean defined over here. Now, how are we arriving at this formulae? You can remember this very easily. Now, variance of x or variance of y is given over here. Say, suppose this variance of y square, I am defining it for one for the variable x and one for the variable y. So, x into y will now give me the value of x into y. So, when I am going to take it as, now this has a whole square. So, I can write it as e of y into e of y. Now, instead of this e of y into e of y, if I am going to change one of them as e of x, then what will happen? This is e of x into e of y. So, covariance formula is something derived from the original formula for your one-dimensional random variable. Just in place of one random variable, we are going to extend it and place it for two variables. So, instead of x square, you write x into x, which can be replaced as x into y for two variables. E of x square is e of x into e of x. So one of it you replace it for y. So you have e of x into e of y. The next concept is going to be correlation of x and y. Correlation is going to be the degree of measurement of the adjustments or the relationship between the random variable x and y. How do you define it? As covariance of x comma y by sigma x into sigma y. Covariance is something which we saw in our previous slide, e of xy minus e of x into e of y. What is the sigma x? Sigma x is nothing but square root of variance of x. And what is going to be sigma y? Sigma y is nothing but square root of variance of y. So variance of x and variance of y we have defined in this formula. Variance of x is e of x square minus e of x the whole square. Variance of y is e of y square minus e of y the whole square. And now we have defined e of x over here. But how about e of x square? E of x square is nothing but how many variables are there? Only one random variable. So it is integral one integration x square into f of x dx. Similarly, if you want e of y square, only one random variable y is involved. So one integration y square into f of y dy. So making use of this formula, you can estimate e of x square and e of y square, subtract it from the means square, get the value for your variance and variance y. Now, when you take the square root of it, you will be getting sigma x and sigma y. Notice a point that variance will always be positive in nature, but your covariance can be either positive or negative, or it can be zero. So it has a possible combination of all three, but variance will always remain as positive. This rho, which is going to be the correlation, the degree of measurement of relationship between the variables x and y, has a range between -1 less than x rho comma x comma y and less than or equal to 1. So it can vary only between -1 to +1. If you're getting the answer as anything apart from that, then we need to be very cautious enough to go and check for it. So rho can also take the values in negative or in positive, or it can be equal to 0. The value taken, if it is going to be equal to 1, you say it is going to be perfect positive correlation, which means an increase in x causes an increase in y, or a decrease in x causes a decrease in y. When it takes the value -1 and moves over here and might takes a -1, the value -1 is called as perfect negative correlation. So what does this mean? An increase in x causes the decrease in y, or a decrease in x causes an increase in y. So when the two variables move in the same direction, they increase or decrease together, you call it as positive correlation. And when the two quantities move in the opposite direction, an increase of one causes the decrease of other, then you call it as a negative correlation. Keep in mind the range is always between -1 and +1. Thank you.